Objective 5. Solve polynomial equations. Whenever you have solve, it is a very significant problem. And if you think about solve, solving equations, there are various methods depending on the degree of the equation. So if you have a first degree equation that you're trying to solve, you're going to try to isolate x and do the same thing to both sides all the way down. If you have a second degree or quadratic equation, then you're going to use quadratic formula or maybe factoring. But then when you get to higher degree equations, like we are here in 4.5, objective 5, it takes still a different method. Now, I have been talking about how this is the core of this section, objectives 4 and 5, and I've also made a passing remark that they're actually the same problem. So we'll see how that works. Okay, so here's a fifth degree equation in one variable x, and we're trying to solve it. We are trying to get the values of x that satisfy the equation. And if those coefficients look familiar, then you probably saw the last video in which we did this problem. This problem was find the zeros. Okay, so now we're doing solve, and earlier we were doing find the zeros of this function, which was also fifth degree and had all the same coefficients. Okay, and so all of this, which is called f of x at the time in the last video, well, all of this is really f of x. All of that is f of x. And f of x is set equal to 0. Now, that might ring a bell because what is a 0? A 0 is a value of x that makes f of x 0. And if you think about it, the zeros are exactly what we're trying to do when we solve the equation, in this case, because we're trying to make f of x 0. And whatever values of x do that will be our solutions. Well, we've already found those, haven't we? What did we do? We used the Rational Zeros Theorem to get all the possible rational zeros of f of x by looking at the constant, looking at the lead coefficient, making all possible fractions of the type factor of the constant over factor of the lead coefficient. And 1 was one of those. And of course we had looked at the graph also and looked at the x-intercepts and suspected that 1 and 3 were going to be solutions, that is zeros of f of x. And we ran the synthetic, got the zero remainder. The division went evenly, meaning that x minus 1 is a factor and that 1 is a solution. Then we took those, the depressed polynomial, 1x to the fourth minus 6x cubed plus 13x squared minus 24x plus 36, and well, we tried 1 again to see if maybe it was a double solution, but we did not get the zero remainder, and so it was not. Then we tried the 2, and again we did not get a zero remainder. But then we tried the 3 as the graph suggested, and we do get a 0 remainder. And you might remember that it actually turned out to be a double solution. That was a case of the graph touching, not crossing. But we know that if you let x equals 1 or x equals 3, you're going to zero out f of x. That is, you're going to get solutions of this equation, and that's the goal. That's what we're trying to find. So if you have a higher degree equation, it takes this process of using the Rational Zeros Theorem, getting all possible rational zeros, and maybe looking at a graph, reducing the thing to enough so that you can use known methods from the past, quadratic formula, whatever, to get the remaining solutions. So, as Sullivan says here, the real solutions of this equation are the real zeros of the polynomial function, because we're setting f of x equal to 0. That's one big 0 right there. And using this result of example 6 from the last video, the real zeros of f are 1 and 3. The real solutions of this equation are 1 and 3. So we could write it the way I wrote it on the previous slide, x equals 1 or x equals 3. Or we could say the solution set is the set 1, 3, where we don't necessarily have to specify that 3 is a double solution. Here's a theorem we'll throw in here. Every polynomial function with real coefficients can be uniquely factored into a product of, you get one of two kinds of factors that you could use to factor every polynomial function. Either linear or irreducible quadratic. And so, this was actually the very problem we were talking about earlier. Here's an irreducible quadratic. It's irreducible because you can't factor it. And then we had two linear factors, and actually three linear factors if you consider the multiplicity of each. And so this is the factorization of f of x that's guaranteed by this theorem. And one more theorem we'll throw in here from Sullivan. A polynomial function with real coefficients of odd degree has at least one real zero. If you have a polynomial function of odd degree, like for example, f of x equals x cubed, well then the end behavior, that is the way it behaves way out on the ends, far away from 0, far away from the origin, is going to be either this or this. In the case of our example, the cubing function, the parent function, or basic function, f of x equals x cubed, has this end behavior. It comes in from below and leaves above. But all of them have one of these two kinds of end behavior. Well, a polynomial function is continuous. That is, you can graph it without lifting your pencil from the paper. And so it's going to have to cross the x-axis somewhere. And that will be our way of seeing that this function will have one real zero because it'll have an x-intercept.